right. Thanks everybody for coming today. This is my very first Python talk. I'm used to giving scientific talks, so sorry if I'm a little terse or anyway. Can everyone hear me fine? Great. Okay, so I'm going to talk today about a modeling framework that we've developed at SunPower that we're calling Carousel. And this is a carousel. And like some of you said, my name is Mikofski, and I'm from SunPower Corporation. So a little bit about me. My handle is Bwana Marco. I spent a couple years in Tanzania in the Peace Corps. Bwana in Swahili means Mr. And there they like all your names to end in a vowel, so I became Marco, and I kind of liked it, so it stuck. Breaking bytes is kind of more for technical stuff, so that my friends don't get inundated with really geeky stuff. They hate that. And then I have this really ridiculous blog. So I did my PhD at UC Berkeley, and I've been doing numerical modeling for a really long time. I don't know if I'm very good at it, but it's really fun. I like it. And currently, I'm at SunPower, where I'm the architect of our performance prediction. And in this context, performance has nothing to do with like servers or websites or anything. Here, we're specifically talking about how much energy our PV systems produce. So SunPower holds the Guinness Book of World Record for commercially available PV panels. PV stands for photovoltaic. We've been doing that for over 30 years. We do residential, commercial, utility scale. We've installed over 2 gigawatts worldwide. And I think this is a really cool picture. This is the Solar Impulse 2, which is the first solar-powered airplane to fly all the way around the world. And it completed that on July 28th this year, and that's the Golden Gate Bridge. And it was entirely powered by SunPower solar cells. They're space constrained, so they pretty much had no other choice than to use SunPower cells. I guess they could have used gallium arsenide, which is a very expensive option, but they chose us instead. Awesome. So here's my agenda, and I'll try to keep on time. So I'll start off with talking about our requirements and some of the challenges that we face. Then I'll introduce Carousel, and then I'll give a little bit of a demo, though it's kind of vague. I'm going to preface this with the disclaimer that Carousel is very much pre-release. And I'll talk about roadmap last, and then I'll give a quick plug for the uncertainty wrapper. And I'll just set the tone here. The overall goal of this talk is to encourage collaboration. We decided to go this route. We saw that there was an absence, and we couldn't find something to meet this need. So that's why we're kind of developing this, but we don't want to go alone. We think that a lot of people could really benefit from this, and we benefit as well. So we all benefit. All right, so challenges and requirements for model simulation. I don't know if we're on time or not. I don't see a clock, but what kind of models are we talking about here? So I work at a solar power company, and we have existing projects, and we have proposed projects, and all of those projects, we need to know how much energy are they going to make every single year for 30 years. It's kind of the amortized lifetime of a power plant, or your rooftop, whatever. And so this is a really large model. It has many factors. In my company, factors is what we call dimensions. Many mathematical expressions, and then there's even conditions within those expressions. When you use this expression, when you use that expression, for example, do you have a snow load, a wind load, or whatever? So it's pretty complicated, and it's in production. Over 1,000 users. I know this is very small from e-commerce, kind of like 1 million people clicking, but we have over 1,000 users every day. These are dealers, these are salesmen, these are researchers coming up with new cell technologies. So this is not a little analytical Jupyter notebook that you can pass around. This is a web application that you go to and you use. So that also kind of sets the tone for Carousel in general. I think that it's really applicable for large scale projects that span a long time and many users. I can see how you might use this for smaller projects, but I don't necessarily think I would recommend it. So what does SunPower need? well, bottom line is we need a bankable model, something that we can show to investors and say, this is how much energy it produces. Well, how did you calculate that? Well, we have this model. It's transparent. It's tested. It's documented. It's stable. It's fast. It's all these things, right? But we're always coming up with new technologies. Now we're coming up with a new type of module. We had a new type of module, new cell technology that just came up a few years ago. We have new tracker systems. So we need a turnkey approach to rapidly develop, maintain, update these models fast. We need to train new people. So we have a little churn, little turnover. People come in, people come out. We expand, we contract. Solar business is kind of a touch and go. I think we're here to stay, but it's still a tough place to be in. And we also have collaborators, people who are using our API. They want to use our software, and they're like, how to use this? And we're like, we don't know. And then we want to integrate with those third-party applications. So we're working with Tendril. Tendril makes applications that talk to your appliances. They say, turn on the refrigerator, turn off the refrigerator, turn on the AC, turn it off, turn on the TV, whatever. So we needed an approach that considered the overall modeling and not just the specifics. So these are some of the challenges of the current state. It's funny, I've been hearing all these talks, and Tracy yesterday was talking about for software carpentry how will be this modeler or data scientist, kind of like the lone wolf in the room. It's like, are you using Git? What's Git? I don't know. And so raise your hand if you've ever experienced any of these. Maybe we'll bond, like my kids do. We're connecting. So there were several coding paradigms and styles, and they were all mixed together with no common guidelines. Anyone ever experienced that? Okay, 100% of the code was proprietary. 0 of the code was from open source. All right, boilerplate procedures were repeated over and over and over again, and there was no leveraging of reusable code. So this is good. No unit test. Profiling and debugging was like finding a needle in a haystack. Implementing new features. So the rest of this kind of goes into what this kind of causes, right? So implementing new features, making updates and bug fixes, they're really difficult and sometimes error prone. Anybody have that problem? You're like, I want to make this change, but I think I have to make it in 4 places, and I'll just search the entire code base for this keyword and see maybe this keyword plus S or this keyword plus lib or something like that. And it's like, oh, there? I never thought it was there. Really? There? Anyway, thank God for GitHub, right? No one knew all of the code well. So this makes training new modelers and collaborators kind of tough, because nobody's an expert. And this is kind of what caused this issue, right? And I think this comes from a business culture. We heard about this from Peter Wang yesterday, this concept that there are software developers and there are data scientists or researchers, right? And you guys don't mix together. A data scientist could never make a Django website. No, right? We get corporate IT, and they just start working on that stuff. Okay, so we put together a spec for this model, right? It's like, okay, the spec will have a PV panel, and the PV panel will have parameters, and there will be an inverter, and we'll connect those together, and we'll calculate the power, right? This is a very 200-page spec. Nowhere in there did it talk about the overall architecture. Nowhere in there did it say it will be extensible. It will have unit testing. It will have auto documentation. It will use source control. Blah, 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 blah. No, never thought of that. So I tried to tell this as a story. I was in reliability where I was working on degradation and the changing trajectory here a little bit. And the R&D guys were like, we want a model that can predict degradation, and we want to be able to throw any formula at it any time we feel like it, and change through output reporting. We want to report for the CEO, for these people, right? I was like, gosh, how am I going to do this? I don't know. So I might be jumping ahead a little bit. I'm jumping ahead. Let's stick here. Okay, so I'll come back to that story later. So we're trying to solve this problem. And so we took some approaches. We're like, well, we'll establish a set of common guidelines. We'll implement some best practices. We'll start using open source. We'll start reusing these boilerplate snippets all over the place, you know. And it's kind of led us to think, oh, well, maybe we need some kind of framework, right? And not just requirements for the model. And so the outcome of that was, well, we'll either adopt a framework or we'll develop one ourselves. And we want to do it in a language that has all the batteries included, as well as a numerical library that's very strong. So obvious choice is Python. So now I'll introduce Carousel. And this is where I was talking about that story. So I was like, oh, how am I going to do this degradation model? These cell guys want to be able to put in any formula anytime. And a friend of mine who worked at LBL at NERSC, he's like, well, you should get design patterns. That's the best computer book ever written, ever. And I was like, so I'm reading through it, and I was like, wow, this is a really big book. How am I going to read this book, right? And I get to this section, it's like on page 26, it's about frameworks. Frameworks versus toolboxes. I was like, wow, this is really interesting. So I start reading it. So this quote's from that book, and if you haven't ever seen this book, I urge you to get it from the library. It's a bit dated, but it's going to be a lot of like, wow, cool. Oh, I do that too. Oh, that's awesome. Totally like that. If you've never felt that and you want to feel that, read this book and you will feel that. So the framework dictates the architecture of your application. It will define the overall structure, its partitioning into classes and objects, the key responsibilities of those classes and objects, and how they collaborate and controls the whole program. A little bit more, if you go into Wikipedia about frameworks, there's a couple of distinguishing features that differentiate them from toolboxes. One of them is inversion of control. In a framework, unlike libraries or toolboxes or normal user applications, the overall program's flow of control is not dictated by the caller, but by the framework, right? So pandas is a perfect example, right? You can use pandas in a bunch of different environments, and you just kind of like grab one tool and you stick something in, you get something out, right? Framework does the opposite. It flips that model and it says, here's what you're going to put in this room, here's what you're going to put in that room, here's what you're going to put in that room, and then you're just going to call me and I'm just going to do magic. Django is a perfect example of a framework. Eclipse, if you ever use Eclipse as a framework. Frameworks are also extensible, so they can be extended. And the rationale for using a framework is the designers of the software framework aim is to facilitate software development by allowing designers and programmers to devote their time to meeting software requirements rather than dealing with more standard low-level details of providing a working system, thereby reducing overall development time. Reducing cruft. This is what it comes down to. This really resonated with me. When I saw that, I was like, oh yeah, that's what we need. That's what I want. And that solved the problem for the degradation model. And that was this guy right here, PV Sim Life. Oh, it doesn't show up on this monitor. It shows up on that monitor. Probably won't slide over again. Oh, wow, that's so cool. All right, so I made this a long time ago. And so come back to today. And we wanted to do this for our energy production model. And I was like, oh, I know the answer. Let's use a framework. And they're like, OK, Mark, we'll try it. So one more time, plug for design patterns, really drive this home. A framework predefines these design parameters so that you, the application designer, the implementer, the computer modeler, the computer scientist, the data scientist, whoever you are, you can concentrate on the specifics of your application, and you don't have to worry about the cruft. Isn't that awesome? So, it's pre-release, Carousel, woohoo! Okay, there were some existing frameworks. Obviously, we shouldn't just go into this willy-nilly. What else is out there already? So, there are existing component frameworks like Django and Flask and many, many, many others for web apps. And these quickly became established. People realized, oh, I'm doing the same thing over. I'm doing, a view or whatever. And so people love these because they automate these boilerplate design patterns. And they result in stable, highly performant, feature-rich web apps and APIs, right? There were model simulation frameworks, too. Simulink is obviously the most obvious of them. But they're really focused on rapid iteration and design and development and analysis. They don't really scale to production. Now, the MathWorks would argue that's not true. We have code generator. We have embedded C. We can do this, whatever you want. And a lot of people do go that path. But it's expensive. And you don't have that much granular control. I mean, if you want to go that way, that's awesome. Do that. We didn't want to do that. So we decided, well, we're going to have to use we're going to have to implement our own. And luckily, we had one because I had already done it for reliability. So we just ported that over, and it became Carousel. So Carousel defines model components and controls the simulation. It's a framework. And so right now I'm going to talk about the structure of Carousel, how it works, how you can make models, and where it still kind of sucks and needs some help, and where it is kind of working for right now. So the way it's structured is you have a big model. And models are made up of layers. And I just made up these names. If they don't work for you, we can change them. Layers are made up of sources. And sources are where you have like the data, the algorithms, the instructions, whatever. So data input and output, those are two separate layers. They collect data from various sources, and they can generate reports. They also propagate units using Pint. Pint has a units wrapper, which is awesome. And Pint is very responsive to pull requests. And they also propagate uncertainty, which is kind of like always the elephant in the room. You know, you're like, the answer is 2. What's the uncertainty? Oh, I don't know. Could be 100%. Could be 200%. I don't know. Anyway, so we need to know that. Bankers want to know that. Data inputs also have something called data readers. And these are methods for retrieving data from different documents. You can think of a document as an object. I like to think of the inputs and outputs as kind of like serializers and deserializers. It differs a little bit from like pandas from Excel in that kind of assumes you already have a tabular format, right? But if you think about it, you get a lot of, let's say you get a report from your fab, right? And they're like, we tested a new cell, you know, and it's going to have like the power in cell B3 and the, you know, a table down here in, you know, C to E, you know, 11 to 22. It doesn't really fit into like a standard. It's its own special unique object, right? And so the data reader might use pandas from Excel, or could use XLRD, or could use NumPy, Gen from text, whatever. And it just kind of coordinates the arguments so that you can pass those into a data reader, and you can kind of lock those in for one particular type of document. And you can create as many data readers as you want, and you can make them as flexible or as narrow as you like. There are formulas. These are mathematical equations and model algorithms, so they can have flow control. They can be whatever you want. They're wrapped with units wrappers and uncertainty wrappers. There's calculations. So calculations are like recipes for something you want to calculate. And basically, inputs, data, and outputs, and formulas, they're all agnostic. So you could reuse a formula many times. So for example, we have a roll-up formula, which is like a pandas data frame group by or summation or something like that. And maybe we pass different arguments into it. So we might roll up energy, we might roll up something else, we might want hourly or weekly. So you can reuse that formula multiple times. The calculation is a map. Which formula, which data map to which args, and what's the return, what output will it map to? Then models and simulations. Simulations is the last layer. It's kind of one of the most powerful layers. It gets access to all of the other layers. And it's where you provide instructions, where you say what you want to show on screen during a simulation, what do you want to write to file. And there, you can also set thresholds when a calculation should be done in a dynamic simulation, when not. I forgot to mention for calculations, there's 2 calculators, static and dynamic. You can add more calculators. And then the model groups everything together. And then every layer has a dictionary called a registry. And it has a couple extra methods. One of them is the register method. Make sure you can't register something twice. And then it also dictionaries are very flat, so it makes the dictionary a little wider so that things can have attributes. And then the way that you extend Carousel is by adding a new layer. So here's kind of a visual of the model. So here's a model. Here you have 5 layers. And then in here you have the sources and some of the things that are in some of these sources, and then the registries. So it's a big visual. So here's how making a carousel model looks to a user. So, excuse me, we have this quick start script. It's kind of like Sphinx quick start or Django start project, whatever. It makes a folder structure for you. This may change just like it did from Django 1.5 to 1.6, who knows. Then what you're going to do, and I'll show some examples later, you're going to create some data subclasses. So the way this all works is by subclassing. I really tried to model this after Django as much as possible. To me, I see this as like Django for modelers. And Django is kind of event-driven. This is kind of more serial. Or there's a DAG actually in there, so it figures out what the dependencies are. You specify the readers, and then you can declare the structure. Do the same for outputs. Do the same for formulas. For formulas, there's something similar to data reader. It's called a formula importer. Right now, there's a Python importer and a num expression importer. I kind of foresee that you could make kernels similar to Jupyter, where you could import from R or MATLAB or whatever, right? C would be really easy to do because there's a C API. Then you create your calculation subclasses, your simulation subclasses. Any extra parameters you want to describe can go in a JSON file. Right now I'm using JSON. I realize YAML might have been better, so maybe we'll use YAML and JSON or whatever. Then you want to create your model. So right now there's already a basic model, so you could just use that, right? Basic model has the basic 5 layers. If you wanted to create a new layer, like a validation layer, then you could create a new model, right? Then you load that model into Carousel, and I'll show you how you do that. You basically just call the model, you pass it the parameter file, you have a model. And then every model has a commands method. Maybe I'll change that to simulate. And you can send the simulation commands through the command method. So you send your simulation the start command, and it starts. How does this look to Carousel on the inside? Carousel's like, oh, I got to load a model. OK, got that. I'm going to import everything and initialize it the way you told me to. OK, now I'll start going through your layers. First, I'll load the data layer. I'm going to load all your data. Oh, you have a data reader. It tells me how to open a file. I'll open the file. I'll get all your data. I'll make your data registry. Next, I'll do that for the output. So right now, Carousel is a little kind of statically defined. You'll notice that it's pretty rigid. This is the easiest way to do things in the beginning. And so you need to define your outputs in advance. And actually, if you think about this, it's kind of good from a modeling perspective, right? The first thing you want to know is, what do I need to calculate? So think of your outputs. There you go. If you want to add some more later, fine. I just did it yesterday. Formulas. So I'm Carousel. I loaded your outputs. Now I'm loading your formulas. Now I'll load your calculations. When I load your formulas, I'll apply the unit wrappers and the uncertainty wrappers, and I'll create the registry, calculations, simulation. And then you send me the start thing. Well, the first thing I'm going to do is I'm going to check your calculations, and I'm going to make the direct, I already forget what it's called, acyclic graph. And I'm going to figure out which ones depend on which. And in your calculations, you actually state this calculation, performance is going to depend on the irradiance calculation. The irradiance calculation doesn't depend on anything. My load shifting algorithm, well, that will depend on the performance calculation and the cost calculation. So it figures that out. And then it's going to do static calculations first. Those could be at different times, but what they basically mean is that they're all independent. So they'll do them all at once. Boom, vectorized. Then it'll do dynamic calculations. Dynamics differ in that right now it only marches over time. But it means that the next time step depends on the previous one. So you could do it implicitly, but that would be a lot harder. Generally, time you just do explicit and you march. And then, so I showed you that PV Sim Life app that I had made many, many years ago. That was a client. We don't have that now. Right now, you do everything in the main workspace, but I'm going to try to do that again. It's just that I thought that was really funny. I don't know if you guys had, who can tell me what this is? Nobody. You're the only one. So yes, I will never use TK again. Never, ever, ever, ever. Oh, but it's so cool, isn't it? No. I'm a solid believer in using the web now. I only use web UIs. If you have not checked out Bootstrap, Twitter Bootstrap, Get Bootstrap, I urge you to do it. It's awesome. Mind is going to be blown. Then you're going to love JavaScript, and you won't never come back to a Python conference. So So PVlib demonstration. Are we OK on time? OK, so PVlib is a Python package that was developed by Sandia National Labs. It's an amazing open source toolbox. This open source revolution is probably one of the greatest things for mankind. So we're following the package overview section that's in PVlib, and it's a very basic calculation of annual PV system energy. What you need in order to run this example is, and currently this only works in my fork, so you'd have to go to GitHub to Mikofski. I have a pull request for this. It was working before, and then I made a bunch of changes in Carousel, and then it broke, and then I made it work again. Oh, and also, PVlib released a new version, 0.4, and they broke their API. That's why I had to do a bunch of fixes. So it does work again. So you will need NumPy, SciPy, numerical expression, Pint. We totally don't follow the dictum that we want to use as little libraries as possible. No, you just have to use all the libraries we tell you to, and that's it. It's on PyPy. So on GitHub, so I encourage you to send us issues and fork it and send pull requests. And there's also some documentation. The documentation could definitely be better. The PVSim Life documentation was a lot more thorough, but this is just one hat I wear, which is fun. So like I said, you're going to call Carousel Quick Start, and then you're going to give your project a name, and this creates a folder structure under a folder called that name. And then it also creates in there a Python package that has the same name but lowercase, right? And that's where you're going to put all your subclasses and models. So we start with the data layer, and you're going to specify, I think in your mind you kind of have to break up your program into structures. You know, I'm going to have all my irradiance data maybe, or weather data. I'll have all my PV module, solar panel module specific data, maybe inverter specific data, and maybe I'll have just like a generic utility data structure. And so then you create data sources based on each one of those by subclassing data source from the core Carousel package. So just like Django, you can declare data directly in the class as class attributes. And then behind the scenes, Carousel uses meta classes to scrape all those up and make them class attributes. Or I guess they already are class attributes, but you know what I mean. Another way that you can do them is you can put them in a JSON file. I don't know which is better. The JSON file is kind of nice because you can change it and reload it with the class when you'd have to quit Python and then start it again, whatever. And then all methods right now, they just kind of have this generic prepared data. If you don't want to use this, you can just say pass, but you have to have that method. And what that does is, like, let's say you read in data, use the XLRD reader, you have data in a spreadsheet, and you have like 6 columns of date stamps, timestamps, right? Year, month, day, hour, minute, second. This happens to us a lot. It's the way that MATLAB does it, right? And you want to group that into like either a datetime object or datetime string, whatever, ISO string. So you can put that in prepare data. You might also need to maybe, one of your fields might be a file name. So maybe you want to open that file and read the stuff out into some data fields. So you can stick that in there as well. So it's just kind of like a cleanup call. And then here are some of the attributes. There's units, is constant, which means that in a dynamic calculation, whether or not it should be indexed at each time step or not. Uncertainty, and you can name which time series it's related to. So it doesn't really have pandas baked in, because pandas doesn't work well with like the units wrapper and the uncertainties wrapper super well yet. I think it will in the future. So that's kind of how you link to a time series. So here's kind of an example. So I'm importing data source from the Carousel core package, and then I'm subclassing it. Here I'm going to make a PV module. I'm going to state it's going to use a Django model reader. So it's going to read this from a Django model, which I've imported here. I don't want it to cache data. So when you load a model, it can cache the data locally to make it faster to load next time. Here I don't want to do that because I only ever want it to come from Django. And then here are my parameters, and I kind of truncated it. And then in my class meta, I'm going to say, what model is this? Well, it's a PV module Django model. And so now I know it's to go get that from Django. What do I want to exclude? A lot of fields in the Django model. You can also, as an opposite to exclude, you can say the fields that you want to include. And so there are a lot of other fields in here. There's like a bunch of coefficients, C0, C1, C2. Those are just going to be pulled in automatically, but their attributes will be set to the defaults. And then here's that prepared data. I'm just going to say pass. I don't need to do anything fancy. The outputs layer is really similar to this. You just basically have to say what outputs you're going to have and what their attributes are. Maybe dynamic sizing will be in the future. And these attributes can change. A lot of these are kind of specific to my needs, but I think they should be more generic. The formula layer, formulas can be written as functions in Python modules or as numerical expression strings using Python numerical expressions. Formulas can be specific or they can be generic, so they could be used over and over again. For example, an integrator, right, is something you might need to use over and over again. Think of like Simulink, they have an integration node, right? They can be short or long, whatever works for you. They can, they're great for wrapping C libraries. So if you import C types, you can import a C library. All return values from formulas go into the output registry. All the arguments can come from either the data registry or the output registry. What? Recursive? I think so. Yeah, definitely. I think the only limit on formulas is that they kind of have to be stateless. So for example, in C, you see a lot of times they pass in like a structure, and then it'll change it, and you see that the formula doesn't output anything. And you're like, huh, where's the calculations go? But in C, they went into that structure, and then somebody else is going to get the structure, and the changes will be there. Here, if you want your changes to propagate, they have to come out from the return. You can't. And I mean, that's by design. Basically, we want this. We want to separate functions and data so that we can basically feed this to the cloud, to a bunch of computers, have them do everything, and come back.
Are units like physical units, like kilowatt hours?
Yeah. Okay. Yeah. You should check out the Pine Toolbox. It's awesome. So basically, let's say your data is in watts, right? But your formula wants to take kilowatts, right? So you just say the first argument input is kilowatts, and Pine automatically converts it to kilowatts, and then it strips the units. And then your function does its little magic because it doesn't know what a quantity object is. It only knows what numbers are, right? And then it spits it out, and then Pine grabs it and said, oh, you said the output should be, kilowatt hours per kilowatt. Boom, done. Are you happy? And so then you never, ever crash a satellite into, like, Mars again. So uncertainty is...
That's actually related to our collisions. So I'm kind of curious here, like how are our collisions at times that handled it all here? You said you're explicitly.
So that's handled in the calculation layer. So the formulas, think of the formulas as objects. They're like bricks, and they don't really have any brains. You just put something in one side, and it comes out the other side. Yes, and I'll show you my formulas. A lot of times my formulas are like one line, like literally here. I'm using a toolbox, the PVlib toolbox, so I'm going to call, this is a clear sky model. I need to massage the data a little bit because it doesn't like arrays. It just wants a scalar. So I take the latitude and longitude, and NumPy has an item call. And so then I can pass them in, and then it spits out a structure. And so I'm going to break that structure or dictionary up into pieces. And actually, it's a Panda data frame. And so then now DNI, GHI, and DHI, which are different types of irradiance, can be shoved into the output registry. And then here's the parameter file that kind of goes with that. And what I'm not showing is in the model, you're also going to subclass formulas and say, I'm going to have, I think this is my irradiance formula module. And so I would create an irradiance formula subclass in my model. So one thing I didn't get to talk about here is uncertainty. We'll talk about it a little bit more. But basically, you take in first order covariance and you output first order covariance in Jacobian, which is the sensitivity. And he uses this great formula, which is basically Jacobian. Jacobian is like your sensitivities times covariance times the transpose of Jacobian. Boom, first order linear approximations. So it's not perfect, but it's better than nothing, which is the current state, and it's really fast. I'll get to that at the end. There's one slide on that. So calculations, again, you're going to subclass calculations. You can declare them inline as class attributes or an adjacent parameter. And the calculations are an ordered list. So it's like baking, right? You know, mix the ingredients first. And so it's a list. And then the next item, let's see if I have an example of calculations. Right, yeah. So they're split up into static and dynamic. And then basically you have a formula. Which formula is it? Arguments. Which arguments come from data? So the frequency argument, that's the hourly data registry item. DT start, that's the time stamp start data registry item. So these are all mapping arguments on the left to the data registry keys on the right. And it doesn't have anything from the output. This formula down here, clear sky, uses timestamps from the output. And then the returns, in this case, it's not a map because this is the name of the return key of the output key in the output registry. So shove that into the output registry, shove these into the output registry. And the uncertainty, that goes into the meta side of the registry. So the registry is a dictionary, but it has this extra little bit to put more stuff in. Then the simulation, right now there's a standalone simulation. I'm hoping that we can create more types of simulations. This is the big conductor, right? And so the things you need to specify here are commands, what you want to show on screen, what you want to write, and that's pretty much it. It gets access to all the registries from the model. And then you create the model. Basically, the model is a list of all your subclasses, what modules and packages they're in, or path. If you want to load it that way, you don't have to give a module and package. You can just say a path. Under the hood, we use the import lib module, built-in module in Python. So here's kind of a collapsed version. You have outputs formulas. I expanded formulas, so I have 3 formula subclasses. Performance is in there. That's the one that had PV module. And then for each one, here I like the module package method really works best for me. Path is good if you have to import a third-party path later and you haven't installed it, or it's not on your Python path, then you can use the path. So it's just very basic, and so that's how you load a model. So here I'm going to go to my project that I created using Quick Start, and then I'm going to import my model, which is Sandia Array Performance Model. And then I create the model just by passing the parameter file to it, the one I just showed you. And now M is a model. I'm going to start that by sending a command to the simulation. Right now the simulation only has one command, start. It has a pause command, but because we don't have the client working right now, the TK client, it won't do anything because you're blocked by this. But, and then it'll run. So in the future, you can use the command line Carousel to do a lot more. So let's see, are we on time? Perfectly on time. It's amazing. OK, so this is the roadmap. And I didn't really prioritize this. I mean, it's great when you have an open source project like this that's funded by a corporation, right? But that also means that the things I get to work on are entirely dictated by my boss, And but there are so many great ideas. Validation layer is one that comes up for me all the time. I made a model and it's not loading. Why isn't it loading, right? Well, it should be easy for Carousel to say, you forgot to specify all the arguments here, or you didn't give units for that, and say that you didn't want to use units. A testing layer. So we talked about earlier how people weren't doing unit testing. Django has a great built-in testing layer. I think that you should be able to just say from your command line Carousel test, and it should run all your tests. You should be able to mock inputs. Like Django has fixtures. A data scrubber layer. For people like us, scrubbing data is important. And here I kind of merged 2 things together. I think it should be easier. There should be a nice, well-documented API. How do I make a new layer? How do I extend Carousel? Just go through these steps. Boom, now you have an extension. Obviously, the client server is a big push for me. I want to be able to start a Carousel process and then just communicate to it through sockets. So that it could be anywhere. So, I mean, we could also use MP, right? And you could just do it locally on your machine. That's fine. That would work too. Oh, right now, everything is taking a dictionary. And one idea I had is, well, why don't we do what Django does and other serializers, make those fields? And what that does is in a dictionary, I could add any key I wanted to, right? And nobody's going to say, that's not a valid key, right? But if you make it a field, it's like a class, and then it will fix that automatically. These last two I've already done, so I've cleaned up a lot of the names and reorganized classes. I've added new readers, so there's an HDF5 reader, there's a database. No, there isn't. So these two aren't done, API and database, but there is a Django reader and an argument reader. And I'd like it to work better with pandas and like SQL Alchemy, other ORMs and stuff like that. Right now it only works with Django. Uncertainty wrappers, this is what you were asking about. So basically, we needed a way to propagate uncertainty. I tried everything, the uncertainties package, AlgoPy, NumDiff tools. All of those require you to change your code, right? Or they don't work on C extensions, third-party libraries that you can't change the code. How are you going to do that? So what we did was we estimate the Jacobian using central difference approximation. Works. You can go to the website. I ran a bunch of tests, and there are cases where it doesn't do a great job. Very few cases, but there are some. Most of the time, it's great. And like I said, it's better than nothing, right? You can preface it and say it's a Jacobian estimate, right, using central difference. It uses that cube root approximation. Anyway, so I vetted it against these guys, and it works great. It's available on PyPy. There's documentation. You can also collaborate on GitHub. And I'm done. Thank you very much. Any questions? Yes? I haven't. Pathos? Yeah, since I developed Uncertainty Wrapper, you go through like, message boards and bug lists, and I've heard so many people rolled their own. So I'm not surprised that there are, you said it was out of MIT? Mike, what's his last name? Okay, thank you very much. Any other questions? Anybody think that they might actually use this for a big modeling project?
So I'm still unsure about like, how you handle numerics and where the actual simulation are.
It's in the calculations. So the calculation layer has two calculators. You can extend this. There's a static calculator and a dynamic calculator. It does the static calculations first, and then the dynamic calculations in the simulation calls those two calculators. And so what it does is it just, after it's done the topographical sort and figure out what the order of the calculations is, it just calls each one, and then it's reading from there. What formula should I use? And then it grabs that formula out of the dictionary. That formula is an object, it's a Python object. It's already been instantiated. It's ready to go. All you have to do is shove in your objects and get them out. So it's calling your formulas, right? So it's calling them serially, one after another, and then it plugs them into the registry, and then it'll get it back at the next. So it's just looping over the time steps. Doesn't solve the time steps implicitly. It's just one after the other. Yeah, for the dynamic part. You could add a different calculator. So that's the dynamic calculator. That's what it does right now. If you wanted to add like an implicit time space calculator, then you could add that as well. So that would be in the calculation layer. You just overload the calculator subclass or class, superclass, and then you could add that. That's a great idea. I mean, I wanted to basically make like a nonlinear calculator. Anyway, okay, I think we're done. Thank you, everybody.